So the content in section 8.5 is actually, of all the sections in this chapter, is probably the easiest content. So I'm going to start off with a little review of section 8.3 and 8.4 and how to do quick graphs of rational and reciprocal functions. And so I'm going to sketch these fairly quickly to just give you a decent review, and try these on your own and then look at my solutions to them. So in this case, I know that we're going to have a vertical asymptote where x equals -2, because that's what makes the denominator equal to 0. And we're going to have a horizontal asymptote because the degree of the numerator and the degree of the denominator are exactly the same. We're going to have a horizontal asymptote at the lead coefficients, the ratio of the lead coefficients, so y equals 4. And so I would go to a coordinate grid and I would sketch x equals -2 for my horizontal asymptote and y equals 4 for my vertical asymptote. And that gives me the framework for this function. And then when I'm looking at exactly where this graph is going to lie, it's not exactly a reciprocal function because we have a degree of 1 in our numerator. And so I'm going to test to see where some ordered pairs lie. And so I'm going to test to the right of my vertical asymptote. So I'm going to plug in -3 and see what my output is. And when I plug in -3, I get -12 over -1, so I get 12. And now I'm going to check, so it's going to be way up here, -3, 12. And so that indicates to me that this branch of it's going to be in the second quadrant based on how we drew our asymptotes. And it's always going to be opposite quadrants, but I'll just test to make sure. I'm going to test a point to the right of my horizontal asymptote, so I'm going to plug in 0 because that's easy. When I plug in 0, I get 0. So it's going to cross through the origin. And so the other branch of this is going to just go right there and pretend that looks good. All right, so for this next one, we have x plus 5. And when I factor the denominator, it becomes x plus 5 over x minus 3. So these two factors would cancel out. So I'm really only graphing 1 over x minus 3. So I would have a vertical asymptote at x equals 3. And once I've canceled, the degree of my numerator is 0, the degree of my denominator is 1, which means that we have a horizontal asymptote at y equals 0. So there's our two asymptotes. Now this reciprocal function, it hasn't been really changed at all, so it's going to be the first and third quadrants, but we are going to have a hole in this one. So I put in my two branches of this hyperbola, and we're going to have a hole at x equals -5. So when I plug in -5 after I've canceled, I get 1 over -8. So I need to go to -5, and I'll do this in red. So -5 and put a hole in the graph right there to show that we recognize that -5 was not in the domain of the original function before we canceled anything. Therefore, there is a hole in the graph right there. All right, x squared minus 9 over x plus 3. This function's going to factor to x plus 3, x minus 3 over x plus 3. These go away. However, -3 is not included in the domain. So really all I have left is the line x minus 3. So y-intercept there with a slope of 1. But I need to go put the hole in my graph where x equals -3. The output would be -6. And so I need to be sure that I show that hole in the graph. All right, 5x over x cubed minus 5x. In this case, the degree of the numerator is 1. The degree of the denominator is 3. Therefore, we're going to have a horizontal asymptote at y equals 0. Now, if I factor, so I get 5x over x and x squared minus 5. So the x's will cancel out, but I need to make sure that I acknowledge there's a hole in the graph at x equals 0. So I'm going to go ahead and do the framework of my graph. And so I'm going to have a horizontal asymptote at y equals 0. I'm going to have a vertical asymptote. I have two vertical asymptotes because x squared minus 5 equals 0, where x is equal to plus or minus the square root of 5. So I have two vertical asymptotes. So let's see, square root of 5 is going to be between 2 and 3, and negative square root of 5 is going to be between negative 2 and negative 3. So right about here, and right about here. So those are the lines x equals square root of 5 and x equals negative square root of 5 are our two vertical asymptotes. So now to figure out where some ordered pairs are going to lie in this, I would probably go to my graphing calculator right now because this is going to be a weird one. But when I plug in x equals negative 3 to the function, f of negative 3 is going to give us an output of 5 over 4. So I'm going to go to negative 3 and 5/4, which will be right about here. So this piece of it, because of where that ordered pair is going to lie, that's going to be a branch of a hyperbola that looks like that, going through that ordered pair. Now the middle part is going to be a weird one, and I actually would go to my graphing calculator later on that. So I'm going to figure out the left part. And so I'm going to plug in 3. And when I plug in f of 3, we get 5 over 4 again. So that's going to be right here, and that's going to come down here. And for this middle part, it's going to be a parabola, and I'm going to just test some points. I'm going to first plug in f of 0. Even though that's going to be a hole in the graph, it'll still tell me where it's going to go through. And where f is 0, it'd be negative 1, looking at the simplified version of this. And then I'm just going to look at where f is 1 and where f is negative 1. So where f is 1, we're going to get 5 over negative 4. And where f is negative 1, we're going to get negative, wait, is it negative 5/4? Yes, it is negative 5/4. And so I'm going to go up here to my graph now and say, all right, well, at 1, I have negative 5/4. And at negative 1, I have negative 5/4. So this should be a parabola going down like that. Now let's go ahead and put the original function into our calculator. So it was 5x divided by x cubed minus 5x. Okay, and so it looks essentially like we just did. We just need to make sure, last thing, that we put a hole in the graph right there where x equals 0. And last one, x plus 2 over x cubed plus 8. Okay, you're not going to remember this very well, probably, but the bottom will factor because it's a sum of perfect cubes. So that's the same opposite, always positive. So the bottom's going to factor to x plus 2 times x squared minus 2x plus 4. And these factors will actually cancel out, and so you end up with 1 over that. Now, we know that we have a horizontal asymptote where y equals 0 because the numerator has a lower degree than the denominator. So we'll go ahead and put that on our graph. And x equals -2 will be a hole in the graph. And at this point, I would actually go to the calculator and plug it in. So we need to keep it in parentheses, x plus 2, divided by the quantity x cubed plus 8. Let's see what we have. All right, so we have this graph that is hugging this asymptote. Let's look back at it again. And you guys, I will let you use your graphing calculator a lot on this. And so let's zoom in and try and see this a little bit closer. The main thing I want to see is that you can find the horizontal and the vertical asymptotes. And if you plugged values in for this one, you would see that it basically hugs that horizontal asymptote the whole time. If you want to plug in specific values, you can. If you want to see what f of 1 is and what f of -1, this will kind of show you what's happening with it. So when we plug in 1, we get 3/9 or 1/3. When we plug in -1, we get 1/7. So we could show those ordered pairs on there, but it's just kind of going along here. I think it comes up a little bit. Not a big deal. It's a good, decent sketch is fine. So we did that last time, and let's go ahead and go on to the lesson of the day. So 8.5, the new content, is dealing with direct variation, constant of variation, joint variation, inverse variation, and combined variation. Now, direct variation you've had in the past, and it's basically just a line, but instead of writing mx, we have this constant of variation that's called k. And you saw it in exponential functions when we did y equals a times e to the negative kt, and k was our constant of decay or our constant of growth. Well, here it's more simple, actually. Direct variation means that you have a line that goes through the origin, if you're talking about linear, and that constant of variation is going to be your slope. Joint variation means that you might be combining two things that vary directly, or one thing that varies directly and one thing that varies inversely, and we'll see how we can put those in equations. Inverse variation means basically you have y varies with x inversely, and x would go in the denominator, but that k is still there. You'd still have to find that constant of variation, and combined means you're combining inverse and direct variation using joint variation. So let's look at some problems. So direct variation, y varies directly as x if there is some non-zero constant k such that y equals kx, and k is called our constant of variation, which is basically just our slope and a line that passes through the origin. So if y varies directly as x, first thing you should say is y varies directly as x, and write down your literal equation. And when y equals -15, x equals 5. So you're plugging that in so that you can find your constant of variation. And so when you do that, you get that the constant of variation is -3. So you go and say, okay, the equation for this particular case is y equals 3x. Then you can answer, find y when x equals 3. So y equals -3 times 3. So y would equal 9. And that's it for direct variation. For joint variation, y varies jointly as x and z if there's some non-zero constant k. So in other words, if it's varying directly with both of them, that means you're going to take k times x times z, and you're going to solve from there. So let's look at a problem with joint variation. Suppose y varies jointly as x and z. So you're going to immediately write down, okay, y varies jointly with x and z. And that means they both just go in like that. Find y when x equals 10 and z equals 5 if, and this is the key information for the first part of the problem, if y equals 12 when x equals 3 and z equals 8. So y equals 12 when, we don't know what k is yet, x equals 3 and z equals 8. So when we solve this, we get 12 equals 24k, and k equals 1/2. So now we know that y equals 1/2 times x times z. I'm writing with my fingers, so this gets very messy. So find y when x equals 10 and z equals 5. And so y would be 50. No, I'm wrong. Y would be 25. Okay, inverse variation is not that much more difficult. So y equals k over x if x varies inversely is y. So r varies inversely is t. So that means r equals k over t. And r equals -6 when t equals 2. So -6 when t equals 2. So in this case, when we multiply by 2 on both sides, we get that k is equal to -12. So our equation is r equals -12 over t. So find r when t equals 7. So r equals -12 sevenths. And that's as good as it gets. Combine variation. Now here's where you get to combine inverse and direct variation. And you're just going to read it and put numbers in as it goes. So it says f varies, and let's go ahead and put our constant in right away. So f varies directly as g. So that's going to go in the numerator. And it varies inversely as h. So whatever it varies inversely with, it goes in the denominator. So find g when f equals 6 and h equals 5 if this. So this is what you need in order to find that constant of variation. So if g equals 18 when h equals 3 and f equals 5. So f equals 5, g equals 18, and h equals 3. So we get 5 equals, the calibration is off on my computer, 5 equals 6k, and k equals 5/6. So our equation here is f equals, and we can just put k out front, 5/6 g over h. And so to find g when f equals 6, so 6 equals 5g, and h equals -5. So I'm going to multiply by -30 on both sides. So that's going to give me -180 equals 5g. And divide by 5 on both sides, and we get g equals -36. So that's really it for this section. So it's kind of a breath of fresh air from the more difficult stuff that we've done.